Hi there and welcome to my YouTube channel. In this video I'm going to share with you a powerful Abaqus plugin that I developed as part of my PhD thesis. This plugin is specifically designed to help you generate 3D tubular columns with socket faces using solid and rigid elements. If you are interested in more details, I've included a link to my thesis and some related papers in the video description below. In this video I'll take you through a step-by-step process of generating a finite element model using this plugin. Whether you are a beginner or an experienced user, this walkthrough will help you make the most of its capabilities. If you are not familiar with the installation and downloading process of an Abaqus plugin from GitHub, I highly recommend you watching my previous video on this topic, found under this name on YouTube. It will guide you to the necessary steps to get started. But before we dive into the details, let me highlight 4 important things about this plugin. Firstly, you will notice that some fields are already pre-populated with predefined data, but don't worry, you can easily modify them to suit your specific needs. Secondly, as this plugin is publicly available on GitHub, it is important to know that it may undergo improvements by both myself and other users. Therefore, please keep in mind that the information presented in this video may or may not be relevant in the near future. For your reference, I will be using the release version 0.2.0 throughout this demonstration. Thirdly, when the model generation is successful, you will see the following reassuring message displayed in the message area. Model created successfully. Additionally, you can verify the job creation as another confirmation of a successful model generation. On the other hand, if an error occurs during the generation process, an error message will be displayed and the model generation will be stopped. These error messages are designed to be clear and concise, helping you identify and resolve issues quickly. For instance, if you forget to define a load, an error message like this will appear. Error no load defined. Load required on at least one face. To avoid encountering errors, make sure to read the important messages that appear in some tabs. For example, in the Load tab, there is a message at the bottom of the plugin. Lastly, by clicking on the Apply button, a new model will be generated and the window of the plugin will still remain open. On the contrary, while pressing the OK button, the window of the plugin will disappear. Now that we have covered these important aspects, let's explore the various tabs and symbols in detail. This will provide you a comprehensive understanding of each symbol and variable used in this plugin. Let's change the model name first to ytTest, and now let's go tab by tab. First, let's start with the Geometry tab. It's divided into 2 parts. One for the column, the top part, and one for the socket face, the bottom part. The column definition requires 5 numerical inputs. The width, BC, the height, HC, and the length or depth, L, also the thickness of the tubular profile, TC, and the external radius, rad, E. The internal radius is determined by the difference between the external radius and the tube's thickness, ensuring that it's always positive. Moving on to the socket face, it requires 3 numerical inputs. The height, HS, the thickness, TS, and the distance between the socket faces, DS. It is important to note that the sum of the distance between the socket faces and twice the thickness of the socket must be less than or equal to the difference between the column's width and twice the external radius. This ensures that the socket faces align with the straight part of the column face, namely this region here. Now let's head over to the Material tab. Here you will find a name field and 2 tables for defining elasticity and plasticity. Next up is the Mesh tab, which offers 2 categories for mesh definition, by size and by number. In the size definition, 3 inputs are required. A global size, G, applied to the center of the column, namely to this region, and along the height or width of the cross section, the height or width. Additionally, there are SB min and SB max. SB comes from single bias in the minimum value and the maximum value, which are applied along the height of the column, parallel to the z-axis in this situation. On the other hand, the number definition requires 2 inputs. RC stands for rounded corners and represents the number of elements assigned to the half of the rounded corners tube, namely this region here. We change the view. It will be this. And also T, which stands for thickness, representing the number assigned to the thickness of the tube's faces. namely these regions. Let's move on to the Low tab. Here you will find a figure illustrating the tube's cross-section along the column face names A, B, C, and D. Each face has a check button and an input field. For example, to add a load on face A, we'll simply check the button and change the value in the input field to a non-zero value. Let's say 1. Let's make it negative to ensure deformation occurs along minus y-axis. Now let's explore the Analysis tab. Here you can select whether to use geometric nonlinearity or not. If nothing is selected, there won't be any geometric nonlinearity. You can also define the stopping criteria and the incrementation values. In our case, since we added a load on face A, let's choose a stopping criterion based on the maximum displacement of, let's say, minus 5 units on degree of freedom 2, which corresponds to the y-axis, of column face A. Degrees of freedom 1 and 2 represent the x and the y-axis, x and y-axis 1 and 2. In the Job tab, you can specify the number of GPUs and CPUs for the analysis process. Lastly, we have the Info tab, which contains information about my PhD thesis, supervisors, the location from where you can download the plugin. Additionally, the Acknowledgements area displays the logos of the institution that supported me throughout my PhD journey. That wraps up our in-depth exploration of the plugin. I hope you find this video informative and helpful. If you have any questions or suggestions, please let me know in the comments below. Don't forget to like this video and subscribe to my channel for more exciting content like this. Furthermore, if you find this plugin useful, I encourage you to utilize it in your work. You can also contribute to its development on GitHub, and it would mean a lot if you could cite the plugin in your research. The DOI of the plugin can be found in the README file on GitHub. Here. Thanks for watching. See you in the next one. Bye.